In this video, give you a very quick review of how to use graphical analysis. So if you ever need some help, hopefully this video gives you some help. So let's open up graphical analysis. Okay, and if you remember, if we're going to enter data manually, we go manual entry. Proper graph, we have to label the axes, right? So we go here to our data set, column options, and here's our x-axis. And I'm going to do a position versus time, a typical study of motion. Okay, and time we measure in seconds. We leave everything else the same. We apply that. We got our table set up here, and our axis is labeled. Let's label the y-axis. And this is my location. We call that position. Okay, and we're going to measure that in, let's just say centimeters, okay? Could do meters, could do kilometers, and we apply that. So we have our axes labeled. That's the first part of a good graph. Now we do need to give it a title. Remember the title so we know what we're looking at here. We edit the graph options. Our title is position versus time. We always do the dependent variable versus the independent variable. Make sure it's just on points, and we can leave everything else the same, and the graph will scale automatically. Great. Okay, so now we have some data that we maybe took, and I'm going to make some up here. Here's an important point. Before we start, I haven't gone anywhere. The point 0, 0. Let's just say 1 second, and maybe we went 1 centimeter. At the end of 2 seconds, and let's just say we went 4.1 centimeter. At the end of 3 seconds, notice the graph is scaling. We went 8.8 centimeters. At the end of 4 seconds, maybe 15.5, and then maybe at the end of 5 seconds, we've got 25.2. Let's add another point here, 6 seconds. And maybe we have 36.5. Let's add one more. 7. And maybe we have 48.5. All right? So we got a lot of points over 7 seconds. We might typically run a lab like this for 10, 15, 20 seconds. So what do we have? We have a labeled graph. We have our data points plotted. Now we have to find a line of best fit. Line of best fit. Let's let graphical analysis do that. Down here are graphing tools. Apply the curve fit. And its attempt at a linear fit is not very good. This looks like it's increasing. So let's try a quadratic fit. And look at that. We're going to apply that. That's a great fit. How do we know it's a good fit? Well, first of all, our error here, let's look at this bottom one, is 0.2. You actually could try some other curves if you think, oh, I could do better than that. But remember, the closer to 0 this is, the better the data fit. So we have a graphical model, and there it is. I can now say at this time here, here's my position. At this time here, there's where I would expect to find it. We now have a mathematical model as well. Graphical analysis did that work for us. And it said y equals ax squared plus bx plus c. That's a very typical general standard model for a parabola. And it gives us what a, b, and c are. And a and b actually are significant enough. They're low, but I would keep them. If these numbers were, say, less than a tenth, I would ignore them and could count them as 0. Okay? But we're going to keep these. And so what do we now have? Well, a mathematical model except for one thing. We don't use y and x in physics class. We use the proper terms. Y would be position equals 1.05 times my time squared. That's what's x plus minus 0.27 times time plus 0.14. So remember, we have to substitute the physics variables in for the y and x. That's a math class thing. What about making this curve a straight line? We said we could take these functions and make them a straight line. How do we do that? Well, I'd like to pull this down to make it a straight line, okay, towards the x. And surely the x is the one that's squared. The y is a linear term. So we leave the y alone, and we're going to square the x-axis. And that should give us a straight line, but let's try that. I could calculate x squared and make another graph, and it'd be linear, but if I go in here, under time, which is the x-axis, and let's add a column we can calculate. Let graphical analysis calculate it. So we want to do times squared, and our units would be second to the second power. Everything else is good here. And now we have to tell graphical analysis, well, do the calculation. So we insert some kind of an expression here. We're asking graphical analysis to square the x term. Well, here we have a coefficient x to raise to some power. Well, that's what we're going to do. We're going to take the x term and square it, and we're not going to use a anything but 1. So here's the expression, 1 times my time, and I'm going to raise my time to the second power. And then we apply that. And now we got a whole bunch of points here. Okay? Look at that. That's just the time squared. But I don't see a graph. Where's the graph for that? Where is the graph for that? Well, the graph is still saying I've got position versus time, not position versus time squared. To do that, I have some choices. I click on the times, and now I can put times squared. And there I got a new set of points, but I got to get rid of this quadratic fit. And there's my points for position versus time squared. Now we're going to apply a curve fit, and now the linear fit works just well. And now we have another mathematical model that says y equals mx plus b. We know that. We know what the slope is, and we know what b. And notice this, when we do a straight line, we all go get something called an r. The root mean square should be close to 0, and the r value should be close to 1. So there's hopefully a good review of how to use graphical analysis, and also how to take a nonlinear function and make it linear. Okay, doke?